Really looking at here is this. This is what's going to be the at-launch aerosol product from OCI. It's what I showed you on Monday, right? So it's basically dark target plus deep blue. You're going to get aerosol optical depth, land and ocean, and you're going to get fine mode fraction. And we talked about what fine mode fraction was, right? Okay, cool. So I was going to show you what, how this works on the inside, but we just don't have time. So we're just going to zoom through this. Okay, it is good. Next time. But OCI has the UV bands, right? And the dark target and deep blue don't use UV. And you're therefore losing opportunity to add information to your aerosol retrieval and get more stuff. So I showed you again this figure on Monday and showing that there's another heritage, that's the OMI heritage. It's the UV, near UV algorithm heritage. And what that gives you is absorption along with the AOD. And aerosol absorption is really important all the way around for climate, for identifying what kind of aerosol it is. Different black carbon amounts have different health effects in your lungs, right? So absorption is a key parameter that we want to get from aerosol. So the idea now, if we combine the dark target, the blue heritage with the OMI heritage, we ought to get more stuff. But I want to show you something about UV. This is a OMI surface minimum reflectivity. This is all the times you don't have clouds, right? Looking down at the surface over a month at 354 in the UV. So I don't know if you ever looked at the globe in the UV before, but if you notice, this is the darkest. The ocean can be dark, but the ocean deserts can be a lot brighter than the land. The ocean is not dark in the UV, especially in the ocean deserts. So, you know, I don't know how much you put your engineers through to get UV on OCI, but I hope you know what you were doing when you did it. Because it's stuff, there's a lot of information there, but it's hard to get. And another reason why it's really hard to get is the Rayleigh scattering. This is Rayleigh optical depth. Andy showed you reflectance, Rayleigh reflectance. This is the optical depth itself. And as you go down to the below 0.4, you just get, the atmosphere gets really, really, really thick, right? So Amir, right, you know, it's just extremely thick. So you're looking through a really thick atmosphere at a very, you know, at a surface on the ocean. It's just not going to be easy. But anyway, that's another story. I wanted to show you this. This is the AirNet from UMBC yesterday while we were on the roof. Suddenly everyone's interested. So we were there, like in this period here. This is the level 1 data. This is all the observations, all the sun data. This is, they did some cloud clearing. They're looking at the triplets, clearing things. So you can see this kind of stuff here disappeared. This was probably clouds. That was before we went up on the roof. It was earlier in the morning. But we were there in here, and you can, it's, anyway, that's what we were. So the data's already there. But I got this because the AirNet we were looking at actually goes all the way down to the UV. It's actually had more wavelengths than I thought it did. It's a more modern sensor. So if we look at the aerosol spectral from yesterday, from the AirNet, that's that blue line with the Rayleigh. Just wanted to give you a feeling for how thick the atmosphere is compared to what aerosol is in the UV. Yeah, it's lambda to the power 4. But sometimes lambda to the power 4 doesn't sink in like a graph like that, right? So there we go. So the point is, in a MODIS or VIIRS aerosol remote sensing, you have a surface over land or something, and the atmosphere is a nice light blue. That's the Rayleigh. And it doesn't matter to a MODIS or VIIRS algorithm that I do, like a dark target algorithm, what height the aerosol layer is at. It's just so, I mean, it matters a little bit, but it doesn't really matter to the retrieval. But if you start working in the UV, like with OMI, now the land surface is darker, but you're much more sensitive to the pressure, and there's a lot more pressure and gas molecules closer down. And so if you have sunlight coming in and the aerosol layer is above, you have a scattering event and it scatters up to the satellite. But you have a lot more chance when you're low down for there to be a lot more multiple scattering before it gets back to the satellite. So it matters a lot. Altitude now matters a lot when you're using the UV for aerosol retrieval, if you go down to the shorter wavelengths. So you can't ignore it anymore. So in the visible, or the visible in the shortwave, we base our retrievals on the fact that we're sensitive to the geometry of the situation, always the geometry, because it's very different every time you change the geometry. The aerosol optical depth, primarily. The scattering aerosol properties, that's why we have to kind of guess what the aerosol size is and stuff like that. And the surface reflectance is really important. And an itty-bitty amount of Rayleigh optical depth. And you can model that really well. But when you move into the UV, you're sensitive to all this stuff. Rayleigh becomes much more important. So you have to model it even better than we can do normally. We're also much more sensitive to absorbing properties of the aerosol and to where and the height the aerosol is, and the surface reflectance a little bit. So it becomes a different problem, right? So traditionally, when we're retrieving aerosol, there were, in the UV, there were 3 free parameters: AOD, absorption, and height, but there were only 2 pieces of information there. So what you had to do is you had to guess something, constrain it, and pull out the other 2 items. And there was uncertainties all over the place. So what they tended to do is they would guess the aerosol layer height based on some kind of climatology or some other information and pull out absorption and AOD. But now we've got this broad spectrum instrument, and we're going to use the visible part of it to constrain the AOD. We're going to retrieve AOD from dark target deep blue, just like we always did, extrapolate it to the UV. Then we know what the UV AOD is. Great. We have a constraint problem. We have 2 pieces of information. We pull out absorption and layer height. So that's what we're trying to do. We're getting there. It's not that hard, but it's the details. The details are always difficult. So this is what I hope to provide to PACE. And it won't be at launch, but I hope to be soon after launch. Single scattering albedo, aerosol layer height, and AOD above cloud. And I'm going to do this at 7 kilometers, not at 1 kilometer, not at native pixel resolution. Why do I do that? Because this is from MODIS. I don't have it for here, but we had 500 meter native resolution and a scene over land, right? Some vegetation, some not vegetation, different things. If I took the 400 total pixels, I took out all the water, all the snow, all the clouds. I was left with 265. It's a dark target algorithm, so I get rid of anything bright. So I had 149 good pixels to retrieve from, to represent the box. But then we got rid of more stuff, statistically. Why? Cloud shadows and stuff that didn't come out of the mass. Nothing's perfect. And so we were left with 44 pixels out of 400 to define the aerosol in this box. And I would give you 1 AOD for a 10-kilometer box. Okay, you're going, wow, that's really stupid, right? I want finer resolution. I want finer resolution, I want finer resolution. I mean, it was like this nagging refrain. So I gave it to you guys. I gave you 3-kilometer resolution. Same idea, but there were fewer pixels to throw away. There were fewer. I would end up with good pixels, and I wouldn't throw away as many. So all the marginal pixels got pushed into the retrieval. And in my 3-kilometer box, I had finer resolution, but more error. This is the difference between MODIS and ARRowNet over land. This is 0. The 10-kilometer product is this black curve, all below 0.05 AOD, which is pretty good. 3-kilometer, it's not as good. The accuracy is not as good. So I'm going to go into OCI, providing a 7-kilometer product because that gives me enough pixels to throw stuff away. And so that's the point that you should keep in mind, that the original at-launch algorithm will be at 1 kilometer for fine resolution. But when I produce the more advanced algorithm and provide absorption, it's going to be at 7 kilometers. But now you see why I do it. OK, here's some examples. This is dust. I'm showing you the ARRowNet stations in the Caribbean. This is the retrieval we can get. And my retrieval is in solid lines. ARRowNet is in dashed lines. I mean, the AOD is like perfect. So that's a dark target retrieval over ocean. When I get the single scattering albedo, the ARRowNet is in the gold lines and different extrapolations. I'm retrieving it here in the UV, extrapolating it to the visible. It's still pretty good. It's still within 0.03. This is smoke event off of California. Lots of variability in the smoke. This is Monterey. There's a USCC prism. There's multiple fires. So there's old smoke, there's new smoke. Very complex, a lot of spatial variability. You can see that with the large spatial variability with these big error bars. And it's not so good, you know, I mean, it's not so bad, but it's not as good as that dust case because it's just all that variability in terms of the AOD retrieval. But in the single scattering albedo at Monterey, it's just about perfect. The solid is the retrieval, the dashed is the ARRowNet. And I'm able to, the blue here is what I'm showing, the matching there. I mean, we caught the north-south gradient down the California coastline in terms of single scattering albedo. So they're showing a lot of promise here in terms of what I'm trying to do. You know, and we are working on it, and but it looks good. But the absorption information is there, and I think we can get it. So I just want to say all these algorithms that I've shown you are multispectral, not hyperspectral. Okay, we're using OCI, but we're using its broad wavelength, not its hyperspectral capability. We could use the hyperspectral with the oxygen A band, like for getting cloud height. We could do it also for aerosol. But that part of the proposal was descoped. There wasn't funding for it, so I can't spend a lot of time with it. None of these algorithms rely on the polarimeter retrievals. None of them, no polarimeter data. So I manage a polarimeter project, but I don't use the data. I think the at-launch algorithms will be as good as what we have now for MODIS and VIRS. There's no reason for it not to be. And this advanced algorithms in process, we're going to retrieve the aerosol absorption. It's there. We should be able to get layer height. We should be able to get AOD above clouds. And that's kind of the whole thing. And I did it in 15 minutes. Yeah.
Is it possible to use spectral AOD to find distinguish between aerosol types? Or
Yeah. We do some of that now. I mean, I definitely can identify the difference between a coarse mode aerosol like dust and others. And when we bring the absorption information, then we could definitely distinguish between sea salt and dust. Yeah, You can draw the quadrant between size and absorption, and we'll be able to go do that pretty well. But it'll be more like types than species.
Yeah.
Excuse me. Yeah, that can be done, yeah.
Do you anticipate that you'll be able to capture pyro-CV or
Capture what?
pyro-CV?
Pyro? Yeah. I don't know. It gets hard. It gets hard because they're kind of a funky thing. It's a
Are the algorithms sensitive enough to be able to identify at the early stages between smoke and cloud, or is that left up?
It's going to be hard. It's going to be hard. If the smoke is absorbing right away, we can use the absorption to do that. But I have to. It may become a research project, a product, not a operational product, because it may need to be applied situation by situation. But I think there's nothing inherent in the instrument or the algorithm that would prevent it. It's forcing it to look at those situations when it wants to go away because it thinks it's a cloud, right? But you could force it. Okay, great. Oh, yeah, go ahead.
When you're constraining the AOD from the visible, do you also need to assume the single-strand albedo will be receiving the AOD? And after that, how do you determine the single-strand albedo after using UV?
Okay, we're doing two extrapolations. We have to move AOD from the visible to the UV.
Yeah, but it's also based on, you have to make an assumption on single-strand albedo on the line, or not?
Not to make that extrapolation. We're doing it on the spectral dependence, right?
So it's depending on your extinction efficiency.
It's depending on that, and like over ocean, I'm retrieving the model also. I'm retrieving the modes, so it's the size. I have the size, and I can extract the AOD. We're assuming the same extinction, right? Yeah, I agree. Now, over land, we are experimenting with a neural network machine learning technique based on AeroNet. Because AeroNet, I have this, 500 stations of all the way, visible to UV, and we are experimenting with the neural network to do it over land because I find it really hard over land to get a good result. With our ocean retrieval, I'm pretty confident we can do it without a neural network. Yeah.
Just kind of curious, because I know like OMI and TropoMI, with their UV stuff, they just use a couple of UV wavelengths, but with PACE, since there are so many more wavelengths in the UV, do you think there will be like extra information you can get for determining like absorbing aerosols?
Okay. Actually, TropoMI and OMI are more hyperspectral than OCI. People who use those instruments laugh when we say our 5 nanometer product's hyperspectral. They just think crazy. There are two algorithms in OMI. One is called the near UV algorithm. It uses 2 wavelengths. One is called UV arrow, and it uses multiple wavelengths through the UV. I have never seen anything coming out of UV arrow that shows that it has any more information than the 2 wavelength algorithm. It doesn't do any better. I just don't think the information's there. It's like with MODIS, over ocean, I have 6 wavelengths, but I only have 2.5 pieces of information. I could do the same thing with 3 wavelengths. Yeah, you had some question? To compare the 7 kilometer product to the 1 kilometer. Yeah. And I would do it at AeroNet sites, so you would have a referee. So, and then it depends what you're trying to do also. Like when I compare a 3 kilometer product to AeroNet, I use a smaller spatial circle around it, because I want to know if that product can actually resolve the finer scale. I know some people who do a finer product and they're still using, 25-kilometer circles around, like, so then why are you doing something at 1 kilometer? You're not testing the ability for the finer scale retrieval. So when you get ready to do the comparison, run it by me, and then we'll see if you get your circles, make it set up to see if you can really resolve the finer resolution information. Yeah.
I remember the L10c does not provide the AOD at 5 nanometer. I was wondering what kind of interpolation method you apply here to derive the AOD at 5 nanometer.
So everything is interpolated. You can either interpolate AeroNet or you can interpolate from our wavelengths, and we do it based on the extinction from wavelength to wavelength in the models.
It's kind of like the AOD is not linear dependence.
It's not linear. It's not linear. So we always do a quadratic fit. It's always a quadratic fit, always.